I am the co-owner of a startup company funded with family, friends, and fools. The name of the company, IGS Research. And my mission is to connect this part of the title with the other part of the title. And this is a very complicated mission. This tech transfer is almost a 0% success rate. I don't want to be skeptical. But I think that it's worth doing this exercise. When people ask me why am I here, there is an easy question. I want to share it with you. It's the one I share with the banks and investors. The money. European funding schemes promote and actually sometimes enforce that companies are present, are sitting around the projects. And I think this is a very good idea. At least for what concerns the company, being in contact with scientists has saved my company. And I am quite fair if I would say that also I contributed a lot in getting other grants, etc. So this is the European project ASPIN in which my company is cooperating right now. And the reason why I am here is try to put these ideas, not putting the emphasis on how does it work, which details are there, but what can we do with it in the present state of the affairs, as we think the samples are working today. And because we are a flexible startup, if you change your mindset, which has happened in the last year, we will adapt to it. We have the tools and the means. Let me show you the battlefield of my company, an IoT company. We are here at this edge. We are the Internet of Things site. We usually use very simple microprocessors, and to be fair, in the last 7 years, we haven't improved much in terms of the CPU. We use the same things. In the Internet of Things sites, though, what has changed dramatically in the last 5 to 10 years is the connectivity of these small CPUs that now can talk and interact with many more devices, and also the algorithms that 10 years ago were simple flowchart diagrams, just very simple if-then-else things, are now being empowered by AI. So we are using the data we collected over the years to make better algorithms that fit within sometimes 2 kilobyte RAM devices and take better decisions now than 5 to 7 years ago when we started the startup. So you see, there is a flow from the Internet of Things, very simple devices empowered by the mathematics of AI, towards the other side of the slide, where there is the high-performance computing, the big boys in this game, Google, Intel, NVIDIA. These guys do everything perfectly. And they are very good at collecting data, processing data, taking decisions, etc. When applying for funding 3 years ago, it was very easy to criticize them, at least to find a breach of opportunity, because they were very energy hungry. For example, when we were all very excited because AlphaGo finally beat a human. That's great, but it took 40,000 watts. Compare it with your 20 watts brain. Average. So, no, average in the same person. So, it fluctuates day and night. So, the point of AlphaGo was, okay, AI is fantastic, but it takes a lot of energy, so we are going to come up with material science and propose much more energy-efficient devices. But Google and the companies have done their homework. And we have, as material scientists, to hurry up. Because in the last years, I show you here a small plot. When you can download the slides, there will be the extended plot. The energy moved in just 2 years from 40,000 watts to 1,000 watts to beat a human with artificial intelligence hardware. And actually, they released the Coral, which is the TPU that you can buy for yourself. You program it with Python, and you can have a TPU in your home for $149, connect it to a camera, and do your image recognition at 10 watts. Energy is important. In the Internet of Things, energy means battery life, how often you have to go to change a device, battery, or maintenance costs. Look that from 40,000 watts to 10 watts, I think the big guys are doing their homework. So this battlefield is getting packed. It's more difficult to get an opportunity to really flash with just a very simple idea. And on the bottom, in between these two, there is an emerging trend in which bio-inspired hardware, which is basically some blocks, hardware blocks that exchanges spikes, electrical spikes between them in a very, very energy efficient way, their consumption is negligible in terms of operation. They can take decisions, but they are still very difficult to train. But the opportunity for research, in my opinion, is try to contribute to these guys with pieces of their puzzle. And actually, when you hear the talks by these bio-inspired guys, they are making calls for material science opportunities in which their SRAMs, which are volatile, could be eventually substituted by non-volatile resistive RAMs or whatever. They're actually having lots of projects in Europe in which companies which have consolidated, iCortex, for example, a spin-off, that consolidated the chip is cooperating with suppliers, material scientists sometimes, of non-volatile memories. Imagine you have a very smart brain but forgets everything when energy goes away. And Internet of Things, the smart city, the smart car, the smart fridge, energy goes away very often. So you need non-volatile memory in all this. Where is copper manganese arsenide? We will discuss it together at the end of my talk. I guess it's somewhere in the middle. But again, I'm not interested in the details, how these, the domains, all these things belong to you. My point is, let's go take a sample. This is the weapon they give me to fight in this battlefield. Take a sample, throw pulses to it, and see what the sample can give to us as an Internet of Things company that builds PCBs and small devices everywhere, routinely. So let's go to the lab. One of the first things we observed is that if you start sending pulses to it, somehow you can make the analogous of a SAM and fire, which is the entry ticket to the show of neuromorphics. I mean, you should have at least one of these features. Simonfire, the leaky Simonfire, could be used, for example, to detect coincidence, that two things happen at the same time. For example, a car that flows through a street and there are two detectors across the street will be counted as a car and not a human if in very short amount of time you boom, boom, step on both detectors, and each one of these detectors generates a pulse that goes, that it has to be coincident. If not, maybe there were two different cars or pedestrian. This is, and I'm borrowing a slide here from Professor Jungberg, this is one thing that has a very clear analogy in biology. Another one, and the one which I am fascinated with, is this erasing. Camille was talking about this erasing possibility, which to me answers the question which pulse was first, which has a lot of implications also in the biological inspired brains, let's say. In this, just to summarize Camille's work in two figures, if you send the smaller pulse first and the larger pulse later, you have some sort of Simonfire, an aggregation. If you do the opposite, you get an abrupt decrease of signal, of this resistance or voltage if you are measuring already in the PCB. So, in a company of Internet of Things, which I used to recognize patterns every day, CO2 patterns, intrusion patterns, cats and dogs, everything, these are two very different features. Actually, this abrupt drop here is a unique feature that says that this pulse has happened, the red pulse has happened before the green pulse, and in a very short amount of time. So I have a way, if I hunt for this feature, and I can hunt it with basic analog electronics, or with very simple CMOS as well, of course. If I hunt for this feature, I can make a detector that can tell me which pulse was first. If I have two independent sources of pulses and I tune the height. How can this be important? Just showing you a life or death case. Two cars going one against the other. I think this is not UK driving, this is European driving, if there is some people from Cambridge or Nottingham around. I put the detectors in this way, and this car will hit first the red one, then the green one, boom. I see this feature. I have this car going first over the green one, which is the small one, and then over the red one. I don't have that feature. You see, sometimes you struggle. You think that it's going to be so difficult to apply something. This is the magic of these grant schemes in which an entrepreneur is sitting with scientists from day one. Something which apparently had no use is answering a problem which I am being paid to solve. And 99% of my customers never ask me if this is quantum mechanical, magnetic, photonic, kamehamic, Pokemonic, or whatever. You understand? So the first step is to build a PCB that we will deploy, and we'll give answers to specific questions. I will have 2 pulses in from these 2 independent sensors. I will work with very basic analog electronics to be consistent with this brain-inspired scheme, which aims for very low energy consumption. And I'm going to insert here the holy combness, copper manganese arsenate. It's actually here. And I'm going to make just a circuit that makes a pulse when you go over a threshold for the Simonfire case, or launches a pulse when detects a falling edge over a threshold. So pulses in, pulses out, like those objects in the bottom of the first slide, which were bio-inspired, exchanging pulses. That's the mantra for this low energy consumption. So we had this device built, and I'm going to show you a video. Oh, it's working. So can we check car direction? We have 2 sensors deployed at the entrance of this parking, and the car is going in one of the exiting, for example, over the one and the second pump. This is raw data from the PCB using 1 copper manganese arsenate sample. Okay, then the car turns around. There we go again. You saw the falling edge before. Now we are going on the same sample, on the same parking. The opposite way, we don't see the falling edge. If AI can distinguish cats and dogs, or your voice, can distinguish, obviously, the presence of the falling edge. It's very simple. You can do it analog. We do it analog. But we push it a little bit forward. Can we measure speed? This is not a life or death point like before. This is like a 300, 400, or 1,000 euros fact. And again, you see, the price is not set by the component plus 10%. The price is set by the context. So I've heard many criticisms in talks like this that, oh, but your sputtering machine costs a lot. And I said, oh my God, but the guy who pays me 5,000 euros for a speed detector doesn't ask me again if I use this and that, and if we are within a European project which tries to promote one type of research and it's subsidized, you see the point. You have to use the technology in the right context. That's one. We will go to that at the end of the talk. Speed. 2 detectors. If the car goes slow or fast, we will see the 2 peaks happening at different time delays. And from these images here, which are taken in the laboratory at the moment, we can see when the 2 pulses are very close to each other, this feature, which you can capture with a derivative or something, is much more abrupt than, for example, this feature when the 2 things are very separated. So again, with 1 copper manganese arsenate, I could have an analog translator to speed, which means an analog translator. Question?
Yes, I mean, does it make a difference if you take it in the summer or in the winter month? I mean, the relaxation should be different. Do you see it?
Very good point. We're going to relaxation in a second. Relaxation is actually a bonus. We didn't expect it. I don't need to reset the circuit. Because you see, the car goes in, and after a few seconds, it's gone. And for some applications, we need precise determination of the speed, And for that, we need to stabilize the temperature. That's the point. But for many others in the IoT, like sending to Google Maps the traffic status, we can allow, this is one of the wonders of this neuromorphics that Tomasz was talking this morning, we can allow for certain amount of error and don't affect at all our functionality. To plot red, orange, or green in Google Maps, I can allow summer or winter problems on this system. It's going to be changing a bit. If two cars go tailgating, I'm going to miss one car, but this is not going to change, for example, the application of broadcasting the traffic status far away from where cameras are practical, for example. The point is we have a startup that can build PCBs, we have a new material, we just don't think about the domains, these things, we place it and see in the context and in the infrastructure and in the customer base we have already. To be able to select the length, because the length of the detection, we can also play with the amplitude of the pulses. So if you have the pulses very different, you will be able to get a better slope, which means more sensitivity in your sensor, but lower range. But you can adapt. I'm going to close the door a moment. Going to close the door. We can tune the range of this sensor by adjusting the pulses. This is again a bonus. We didn't expect to have tunability. So if you have pulses of very different heights, you have better sensitivity, less range, and the opposite. And this precisely has some correspondence. It's still not direct correspondence with the spike time-dependent plasticity, which is a fundamental function in the learning process in biological systems. Again, this is not I'm not saying that this is going to learn anything. I'm just saying that we have a tool that resembles that. And now let me go to, in my opinion, the most important slide. It's the emergent hardware Turing test. So now I have a system that performs a function. I'm going to close it in a box, and I'm not going to tell you what it is inside. If I can make you believe that this just works, and you don't know if this is a capacitor, a CMOS, Arduino, Intel, and you understand? For me, it's going to be the phase one of the success, because many customers will not care as long as it works. And the second phase of the success, especially important when you try to develop startups in the academic context, is that you have to escape the case in which you are the supplier of an integrator company that resells to the final customer. Because they treat you like a slave, and they will ask for discounts, and then the price matters. Then one transistor more or less matters. But what we did with this startup was, okay, we're going to provide the final solution directly. So the final customer is the one which receives the data, not the product, of how many cars are flowing in that street. At that moment in which you sell services and not products, specific components, the price of car counting is 2,000 euros per year, because they buy the data. This is the data. Again, Thomas' first slide was talking about, oh, how important is the data, because the data now has a value. Actually, the data counts as an asset, tangible asset of my company. All the data is stored. People value the data. So to be able to transit in this tech transfer 0% success stories expectation, it's important to go as far as you go as a service, avoid as much as you can the intermediaries, and make sure that the people perceives your object not based on your science. I know that if you discover the exchange bias or the spin Hall effect, you're very proud of it. But sell the service, not the component. For a small startup of a small size, of course, when you are playing the league with a company, it's another one. But you see, we could just enclose it and nobody will care, because the context sets the price, not 10% plus the cost. What's next? It was here in SPICE 2 years ago when we presented the first USB counter of antiferromagnets. And we had these boards also developed by IGS Research, in which one of the samples of Kamil and Zdeněk would go there, and from your Mac, Windows, or Linux, you could send pulses and see the signals evolving on your MATLAB or Python, etc. I think it was quite a success, and it was featured in many papers and in conferences. But in the perspective of how we are moving in this neuromorphic arena, that had a problem, which is every one of these individual devices would have to be managed by a master CPU. Whereas what we did now is a PCB that uses copper manganese arsenide in such a way that the inputs and the outputs can be concatenated. So we can build in the future, and we are trying to simulate right now at the level of simulation, what could be a good case, a good use case in which a concatenation of 2 or 3 layers of copper manganese arsenide samples, respecting the capacity of Kamil and Zdeněk in producing samples, of course. I cannot go and propose 10,000 synapses or complicated schemes like that. But it's fundamental that we build an object that you can create new functions by just connecting the output to the input. Before we couldn't. And if I could be honest here, when I went to many conferences in which material scientists were talking about the impact of their individual technology there, they were missing this fundamental point. They were showing you something with multiple states, but for just $10 more, like in Pizza Hut, you get the bigger pizza. So for $10 more, make pulses in, pulses out presentations of your data. Because then you inspire engineers to connect these blocks and build using your technology. So that brings me to the end of my talk. This is the summary. We go back to the point. I think that copper manganese arsenide is able to perform in basic Internet of Things, in the smart city context. We can count cars, we can see the direction. We can, for example, use this ability to balance the state of a parking, cars in, cars out, if the conservation of cars is still holding. And we have seen that some leaky Simonfire and this resembling a spike time-dependent plasticity seems to be a feature that we can implement in an analog way, 100%. And about the high-performance computing, this is not an area we are completely far away from it. You will see in the next talks that the speed, and we have seen it actually in Kamil's talk as well, that the speed of the reaction speed of copper manganese arsenide brings it to a place in which probably has no competitor. Or if it has a competitor, it's less crowded than in other areas where I can use commercial products. I think in this area, copper manganese arsenide has to offer its speed. In this area, we know that we have the possibility of making some leaky Simonfire and the learning process through this plasticity. And here, for super simple applications, which pulse was first can open you a door or close you a door or prevent a car going in a highway in the opposite direction by accident. So I want to thank you for your attention. You can download this talk, these slides at igsresearch.com/Mainz19 PDF. But anyway, it's going to be available in the SPICE channel. So sooner or later, check out this channel. I recommend you to subscribe. And if you do before dinner, click the bell icon so that you don't miss any future updates in this channel. By the way, if you like this type of talks in which we do crazy things with Spintronics and the real life, we have another talk here in which we put magnets inside a volcano to measure landslides, or in this talk where we use piezoelectrics and the counter, USB counter, to monitor if the vehicles on top of the sensor were cars, trucks, or just humans. Thank you very much for your attention.